Welcome to the Crazy Hat Chemist. So here we go, doing another video in atomic structures and electron configuration. So let's get started. Bam! So today we're talking about light production from the hydrogen atom using the Bohr model in the visible region of the spectrum. So I want you to pay attention to that really carefully. We are using the Bohr model. We are looking specifically just at the visible region of the electromagnetic spectrum and light production from only the hydrogen atom. So I want you to look at that diagram. That diagram should be familiar to you. I've used that in previous videos as well. The nucleus is in the middle. The ground state electron is the n equals 1, and then it goes n equals 2, 3, 4, 5, 6. And you should see that as the n, the principal quantum number, increases, the orbits get larger and farther from the nucleus. Okay, so we're going to have an electron. This electron here is in the excited state because it is an n value greater than 1. So this electron is going to fall, that's a fall in quotes, it's going to drop from a high energy level to a lower energy level. When it drops from a high energy level to a lower energy level, it will emit light, okay? And that light for this drop from 3 to 2 is 656.1 nanometers wavelength of light. Now, if you recall, we did some calculations of this previously, and those calculations were an energy that was negative, and that is exothermic. But there are no negative wavelengths. So, because of that, we have to have a positive wavelength, and that's the 656 nanometers. This 656 nanometers is in the red region of the visible spectrum, and it's from n equals 3 to n equals 2. Let's try another one. So this electron is in a higher energy state, that's n equals 4, and this one is going to fall or drop into a lower orbit, and that lower orbit is n equals 2. As it drops, it's going to emit light that is relative to the distance of fall. Okay, and in this case, it's going to be the green wavelength of light at 486.0 nanometers. This is from n equals 4 to n equals 2. We actually previously, in a previous video, we made this calculation. And you should see that Niels Bohr and his calculations and the that he expected and the observed were almost exactly the same. Okay, let's do another one here, and this one here is at n equals 5, and it's going to fall from n equals 5 to n equals 2, and then a light is also going to be emitted here. This one is in the blue region, and this is 433.9 nanometers. That's going from 5 to 2. Okay, and let's do one more here. This next one here is going from n equals 6 to n equals 2, and it's going to emit light in the violet region of the visible spectrum, and that's 410 nanometers, 410.1 nanometers, and that's from n equals 6 to n equals 2. You should notice something about all four of these. These are all in the visible region for the hydrogen atom, okay, and the other portion of this is they are all from high of something to falling of n equals 2. That's very critical. That is in the visible region. If they went from high to n equals 3, then that would not be in the visible region. If they went from high to n equals 1, that would also not be in the visible region. So all the red electrons are high in energy, and they are going to the violet ones that are lower in energy, as far as the diagram color that you have here. You should understand this correlation between energy, frequency, and wavelength. High energy correlates with high frequency and short wavelength. And you should see that with the red light and the violet light that's coming out on this atom here. So if you specifically look at the red light, that is going from n equals 3 to n equals 2. That's a short drop, and that's short energy, a small drop in energy there. Okay, that's a short frequency, and it's a long wavelength. Counter to that is in the violet region. If you look at the violet light, that is n equals 6 to n equals 2. That's a large drop, and therefore you have a high frequency, high energy, and a shorter wavelength. 410 is shorter than 656. Okay, so that's all specified right there. With a large distance of fall is equal to a high energy, high frequency, short wavelength, and also the small distance of fall is equal to low energy, low frequency, and a long wavelength. Okay, you So I just pointed those high correlations between the calculated and the experimental value. Okay, these are the observed values, and we calculated one of them already, and that was in the green line. Now what I need you to do is I want you to look at the previous videos, and I want you to calculate the other wavelengths of which I did not give an example for. So I calculated the one with the green wavelength of light going from n equals 4 to n equals 2. You need to do the one from n equals 6 to n equals 2, and n equals 5 to n equals 2, and n equals 3 to n equals 2, and verify that you get these wavelengths of light. That's very critical. I guarantee your professor, your instructor, will have you do one of these. Okay, that was another crazy video here. I hope you enjoyed it. I'm wearing a crazy hat. If you like that video, give me a thumbs up. If you like what I do here for the chemistry, give me a subscription on my YouTube channel, and I'd greatly appreciate that. I'll see you next time for more cool chemistry videos. Bye now.